Hi. So in the last session, we discussed, we had an overview of Hamiltonian dynamics. We discussed the concepts, the ideas, what we mean by Hamiltonian, how to obtain the Hamiltonian, and the connection between the Hamiltonian and the total energy, which we can use in some problems, and also the relation between conservation theorems and cyclic coordinates from the viewpoint of the Hamiltonian formalism. Okay. So today let's go on to doing some problems, all right, some of the standard problems that we use in Hamiltonian mechanics, all right. So we'll obtain the Hamiltonian in Cartesian coordinates, polar, cylindrical and spherical polar coordinates, and we'll also discuss the Hamiltonian for a charged particle in an electromagnetic field. So in these notes, I have given the step-by-step procedure of obtaining the Hamiltonian, starting with the Lagrangian. Okay. I will also, as we discuss, I will also show that these problems, or most of these problems, can be done in an easier way by identifying the Hamiltonian with the total energy, that is H is equal to T plus V. So that's the easier way of doing it, and in most of the problems that we will see, this method can be applied. All right? There are situations where the Hamiltonian cannot be written in the form T plus V. Okay? Such cases include the cases where the potential depends on the velocity, or if the transformation coordinates depends on time explicitly. All right? So the transformation equations between the coordinates and the generalized coordinates, if it depends on time explicitly, all right, then we cannot use that particular method. But let's look at these examples, and then we can solve more problems. Now in an examination, you might be asked to obtain the Hamiltonian of some system. Okay, they may give you the Lagrangian and then ask you to find the Hamiltonian. So let's do the simplest case, the Hamiltonian in Cartesian coordinates. All right. So let's do it in the traditional way, in the lengthy way first, and then I'll show you that this can be obtained just by the identification that Hamiltonian is the total energy here. Okay. So we have the kinetic energy, which is half mv square, which is half mx dot square plus y dot square plus z dot square. Okay, that's the kinetic energy. And the potential energy, we write it. Okay, let's say that the potential energy is only a function of x, y, and z. There is no velocity dependence. All right. So here the generalized coordinates are the Cartesian coordinates. The Lagrangian is T minus V, which is, this is the kinetic energy, and that's the potential energy. Okay, and we need the Lagrangian because in the Hamiltonian formalism, the momentum, the conjugate momentum is important. All right, so you can find the conjugate momentum corresponding to x, we can find the conjugate momentum corresponding to y, as well as the conjugate momentum corresponding to z. So we'll need this. Okay? And the relation for that is Pk is equal to dou L by dou Qk dot. Okay, specifically we can say that Px is equal to mx dot, etc. Okay, that's what we have here. Px equal to mx dot, all right, and what we need is actually x dot in terms of px, because in the final Hamiltonian that we obtain, all right, in the final Hamiltonian we don't need any x dots or y dots. Okay, we'll have to get rid of all these x dots or generalized velocities in favor of the generalized momentum. Okay, so we say that x dot is equal to px by m. Okay, this is what we mean by inverting the equation. All right, in our theory session we had discussed this thing. We said that pk is equal to dou L by dou Qk dot. This relation is known. All right, now you can, by inverting this equation, by constructing this equation and inverting or solving for Qk dot, you can obtain Qk dot in terms of p. That's exactly what we have done here. Okay. Similarly for y dot and z dot. Okay. Now we write the Hamiltonian, it's summation over k, pk Qk dot minus L. Okay. The summation I have put here explicitly. Yeah. Okay. So this is the definition for the Hamiltonian. So this means that, now this is the general way of doing it. All right. So if you want to find a Hamiltonian of any given system, this is the standard procedure to do this. This procedure always works. Okay. So we just substitute here. Okay, it's pk Qk dot. So it is mx dot x dot plus my dot y dot plus mz dot z dot. All right. So in terms of px, so we write it here, px x dot, py y dot, pz z dot. All right, and this is simply a Lagrangian minus L. Okay. All right. Now we can actually start by substituting for x dot here. right? Because we have already found that x dot is equal to px divided by m. So it becomes px square divided by m, py square divided by m, pz square divided by m, and here also we substitute for x dot, y dot, z dot in terms of px, py and pz. Okay, that's what we do here. It's so we have x dot is equal to px divided by m, or x dot square is equal to px square divided by m square. Okay, that's what we substitute here. There's an m already here, so you have 1 by 2m px square plus py square plus pz square, and you have v of x comma y comma z. Okay, there are no velocity dependent terms in this example. Okay, so this is 1 by 2m px square plus py square plus pz square plus v of x comma y comma z. Okay, now you can also obtain the Hamilton's equation using this formula. All right, qk dot equal to dou h by dou pk, and pk dot is equal to minus dou h by dou qk. This means that x dot is equal to dou h by dou px, etc. All right, etc. Now we can actually obtain this Hamiltonian in a much quicker way, because we observe that the velocity here, the potential energy here is not velocity dependent. All right, we don't have a velocity dependent potential. All right, and there are no transformation equations involving time explicitly. Right, so we can just, as we have seen in our theory session, we can just write the Hamiltonian. Let me write it like this first. H is equal to t plus v. Okay, H is equal to t plus v. Now, okay, let me find some space here. So we can write it like this. We can simply, so this is the Lagrangian, so we can write H is equal to t plus v. So that's equal to half mx dot square plus y dot square plus z dot square plus v. Okay, that's an energy function, so to speak. Remember that this is not the Hamiltonian. This is not the Hamiltonian, because the Hamiltonian has a different dependence. The Hamiltonian should not involve any x dot, y dot or z dot. It should not involve any qk dot. Alright, so we will have to use this relation. Okay, so we can say that px is equal to mx dot by this relation. Okay, dou L by dou x dot is mx dot, or x dot is equal to px divided by m. Okay, we can substitute that here for each case, so it becomes half m. Okay, what's x dot square? It is px square divided by m square plus py square divided by m square plus pz square divided by m square plus v. All right, now this is the h thing, this is the energy function. Now this is our Hamiltonian, because now we have gotten rid of, all this x dot, y dot and z dot in favor of px, py and pz. All right, so this is our Hamiltonian. As we see, it depends only on px, py, pz and xyz. All right, so that's our Hamiltonian. Now, we can of course write it in a slightly simpler manner. So this becomes 1 by 2m px square plus py square plus pz square plus v. Okay, so a common mistake that students commit when doing this is they write this as the Hamiltonian, okay, which is not the case. In your Hamiltonian, you should never have any of the q dots. Okay, so if you remember that, this is easy. You see that it's just one step. All right, to write the energy function t plus v, and then just substitute for x dot, y dot and z dot in terms of px, py and pz, and you get the Hamiltonian. All right, so this is an example for a case where the Hamiltonian can be directly equated to the total energy. All right, so the problems can be done quickly, but the general method is what I have given in the slide, because you may not be able to write h equal to t plus v for all problems. All right, so this is the method that you should practice a little bit more, because if in case you are in doubt about the given system, whether it's t plus v, whether which is t and which is v, etc., you can always start with this formalism, and then you will get the correct answer. All right, but if it's really clear that the Hamiltonian is the total energy, all right, in the case that there are no transformation equations involving time explicitly, or there are no velocity dependent potentials, okay, then you can always write h equal to t plus v. Okay, t plus v. All right. Now the Hamilton's equations are just this: x dot equal to dou h by dou px, and y dot is equal to, all right, so x dot equal to dou h by dou px, or we can write x dot is equal to px divided by m. All right, because h here this is your h. Okay, so if you do dou h by dou px, what you get is px divided by m. All right, so that's x dot. That's x dot. Okay, similarly, you can find px dot. Px dot is equal to minus dou h by dou x dot. So dou x. All right, there's a symmetry. It's not exact symmetry. It's that there's an extra minus sign when you interchange x and p. All right. All right, so you see that x dot equal to px by m. Similarly, y dot equal to py by m and z dot equal to pz by m, and px dot equal to minus dou h by dou x. All right, and the only x dependent term is the potential, so it's minus dou v by dou x. All right, so this you might already remember that in the Cartesian case, this is simply the force. All right, px dot is force. Okay, and obviously the force can be derived from the potential. Okay, in this manner. This is what we use in Newtonian things. This is actually Newton's second law. What you see here is the Newton's second law. Okay, so they are all equivalent, and there are some advantages of going into more abstract thing called Hamiltonian. Okay, now we can also do it for polar coordinates. All right, we can also do it for polar coordinates. Okay? We have done the Lagrangian for polar coordinates. It's half m r dot square plus r square theta dot square minus v of r comma theta. All right, so we are talking again about a potential which does not depend on the velocities. All right, so if you look at the transformation equations here, so we know that x equal to r cos. So we are talking about polar coordinates. So x equal to r cos theta and y is equal to r sin theta. So this we have x and y there, and this distance is r. This is the point that you want to describe. This is theta. So x equal to r cos theta and y is equal to r sin theta. R is this length. All right, from the origin to that point. All right. So you see that the transformation equations do not involve time explicitly. You don't see any time in here. Okay. Also the velocity, so the potential energy is velocity independent. All right. So you can simply write h equal to t plus v. All right. So in this slide you can check that, and you can try doing it. I have written down it in the usual form. H is equal to summation over k pk qk dot minus l. You can do that, substitute for r dot, etc., and then you will get the answer. All right. But since we are recognizing here that the transformation equations do not involve time explicitly, and the potential is a simple function of r and theta. Okay, so in this case we say that we can write h equal to t plus v. Okay, let's first write the energy function. Just h is equal to t plus v. That's equal to half m r dot square plus r square theta dot square plus v of r comma theta. Okay, that's the energy function. Now what you need to do is that you need to get rid of this r dot and theta dot in favor of p r and p theta. Okay, for this we need to find p r and p theta. P r is dou L by dou r dot, that's equal to m r dot, and p theta is equal to dou L by dou theta dot, that's equal to m r square theta dot. Okay, so from here we can find r dot is equal to p r divided by m. Okay, and theta dot is equal to p theta divided by m r square. Okay, from here you see that theta dot is equal to p theta divided by m r square. Okay, now we just substitute theta dot and r dot in here in terms of p r and p theta, and we have the answer. All right, so if you see that, so the Hamiltonian h is equal to half m, it becomes p r square by m square plus, okay, r square p theta square divided by m square r square, right, plus v. Okay, what does this become? It becomes 1 by 2m p r square plus p theta square divided by r square plus v of r comma theta. That's the Hamiltonian. Okay, it's not very difficult. All right. Okay, so you see, you can look at these things. You see that there's a p theta square divided by r square here. Okay, because whatever appears here should have the thing that appears here inside should have the dimensions of a velocity, a linear velocity. All right, so you'll have a conversion factor or a correction factor in this form, and that's exactly the factor that appears in the denominator. Okay, All right, so if this is an angular momentum, for example, all right, we need, let's say that this, whatever appears inside this should have the dimensions of a linear momentum. Okay, PR already has the dimensions of a linear momentum, so fine, but P theta is the angular momentum. Okay, so the corresponding linear momentum we can simply write, if the, in some cases we can write, for example, P theta, or L as we call, L is equal to R, this L is P theta. Okay, P. Okay, this is the linear momentum. Okay, so the P can be written as P theta divided by R. Okay, that's exactly what we have done here. This P theta is actually the angular momentum. P theta has the dimensions of angular momentum in here, and P theta by R has the dimensions of a linear momentum. Yeah, similarly, you can find the Hamilton's equation. You know how to do that. R dot equal to dou H by dou PR with a minus sign. And also for PR dot, and so R dot equal to dou H by dou PR with the minus sign, and PR dot equal to minus dou H by dou R. Okay, there's no minus sign here. I think that's a mistake. I'll correct that in the slide. R dot equal to dou H by dou PR, and PR dot equal to minus dou H by dou R. Okay, so this is wrong. You should remember where exactly the minus sign comes. Okay, so for this we don't have minus sign, right? X dot equal to dou H by dou Px, and Px dot equal to minus dou H by dou X. Okay, so R dot equal to dou H by dou PR. No minus sign there. R dot equal to PR by M. You get this, all right? PR dot equal to P theta square by MR cube minus dou V by dou R. Okay, just take the derivative with respect to R and you get this answer. Okay, you can try that and you can complete that. And again in cylindrical, let's go to cylindrical polar coordinates or cylindrical coordinates. Okay, so transformation equations are x equal to r cos theta, y equal to r sin theta, z equal to z. Okay, you might be familiar with the cylindrical coordinates. All right, so we have got this height. Let's say we need to talk about a point here. Okay, so this height we can call it as z. Okay, and this distance is r. All right. Okay, and this angle we call as theta. Okay, so with that we can write, and this is x, and we take this direction as y, and this is z. Okay, just by looking at this you can see that x equal to r cos theta, y equal to r sin theta, and z equal to z. All right, so you see that the transformation equations, these are the transformation equations between the generalized coordinates and the Cartesian coordinates, and they don't involve time explicitly, and we are talking about a potential which depends only on x, y, and z, or only on the coordinates. All right, so again we can write h equal to t plus v. Okay, so we can so we have got the Lagrangian here. Okay, we have already done this Lagrangian. As I said, this should have the dimensions of a linear velocity inside the Lagrangian. So it's r dot square plus r square theta dot square plus z dot square minus v. You have got the Lagrangian. You find the momenta PR, and you can solve that for r dot. So you get r dot equal to PR divided by m. Similarly, theta dot equal to P theta divided by mr square. Z dot equal to Pz divided by m. All right, how do you do this? You just find, for example, P theta. For example, you can do this. P theta is equal to dou L by dou theta dot. And what's dou L by dou theta dot here? It's equal to, you've got a half m here and an r square. Okay, and that's 2 theta dot. Okay, so it's m r square theta dot. That's P theta. You might be familiar with this thing. It's m r square omega, the angular momentum. Okay, so from here you can find theta dot is equal to P theta divided by m r square. Okay, and z dot is equal to Pz divided by m. Now we can we can find the Hamiltonian in this way, and you see that it's equal to P r square plus P theta square by r square plus Pz square. Okay, you see that PR and Pz already have the dimensions of a linear momentum, and P theta is an angular momentum, but P theta divided by r has the dimensions of a linear momentum. Okay, So these things are standard examples. You will be doing more problems. I will be giving you more problems to practice, especially those asked in the previous examinations. Okay, you can also find the Hamilton's equation. So there is nothing particularly complicated here. So I won't go into each steps. You can look at these steps, or you can actually do them by yourself and get some practice. All right, it's important that you get quick with these sorts of things. We can again do that for spherical polar coordinates. All right, let's not spend too much time on this. We already know the transformation equations here. We already know the Lagrangian because we have found the Lagrangian before. All right, it's r dot square r square theta dot square plus r square sine square theta phi dot square. All right, so without actually applying these transformation equations, we can come to this what is a Lagrangian. Okay, I think we have already discussed it in Lagrangian formalism, because in spherical polar coordinates, as I said, whatever appears here must have the dimensions of linear velocity. Okay, so if you look at this, what's r dot? R dot has the dimensions of linear velocity. Theta dot does not have the dimensions of a linear velocity. Okay, you can look at it like this. Let's talk about spherical polar coordinates. So we have got some particle here. This we call as r. Okay, this angle with z we call as theta. That's why we have got z is equal to r cos theta. Okay, and this angle we call phi. All right. Now, if you imagine a small difference in phi d phi. Okay, if you imagine a small change in phi d phi, we know that from this geometry or from trigonometry, you see that this length is actually r sine theta. Okay, this length is r. All right, so this is r sine theta. So if there's a small change phi, there's a small change d phi. Let's say there's a small change d phi. Okay, I'm just drawing it very roughly, but we have already seen these things. If you have more questions, you can ask. So if you look at a small change d phi here, okay, what's the corresponding change in length? That's equal to this length multiplied. Let me write it more clearly here. Sorry. Okay, there's an easy way to remember these things. Let's just draw these things. This is r theta. This angle is phi. Okay. Now, and by trigonometry, we know that this length is actually, this is r. Okay, this length is r. So this has to be r sine theta. Okay. Now, suppose there's a small change d phi in the angle. Right. What's the corresponding change in length, or what's the corresponding displacement? Right. If this is d phi, okay, if this is d phi, then we know that this length is r sine theta d phi. Okay, this displacement is this length multiplied by this angle. That's exactly what we do here. If there's a small change in theta d theta, okay, the length here is r d theta. Okay, so this is r sine theta d phi, and the corresponding velocity is simply r sine theta phi dot. R sine theta phi dot. That's why we have got r square sine square theta phi dot square here. All right, you just divide it by dt and you get r sine theta phi dot, etc. So I think we have already discussed these things in the Lagrangian. You don't have to go through all these transformation equations to find this Lagrangian. All right, you can directly do that. All right. So that's the Lagrangian. Now we can write the h is equal to t plus v. Okay, half m r dot square plus r square theta dot square plus r square sine square theta phi dot square plus v. Okay, that's your h function. Now you have to substitute for r dot, theta dot and phi dot in terms of the corresponding momenta. For that, we find p theta, p r from here. That's equal to dou L by dou r dot. You invert this to find r dot in terms of PR. Okay. Similarly, we know that P theta is equal to dou L by dou theta dot. You find this and you solve for theta dot in terms of P theta. Similarly, you find P phi is equal to dou L by dou phi dot. Okay, and you invert this to find phi dot in terms of P phi. But you will see a nice pattern here. The final answer, you have got the linear momentum thing, it's PR square. Okay, here we have got P theta square, the angular momentum, divided by the corresponding length. Okay, in this case, this is theta, this is r. Alright, so you have got a p theta, an angular momentum, divided by the corresponding length. Alright, so there's a change like that, and the corresponding length is r, so it's p theta divided by r square. Okay, similarly, if you look at p phi, there's an angular momentum p phi, and there's also this corresponding length is r sine theta. So it's p phi square divided by r square sine square theta. Okay, there's an easy way to remember these things, but just for the sake of completeness, I've done all the steps here. Okay, so after some practice, I think you can directly start by writing the Hamiltonian in spherical polar coordinates in this form. Alright, it's pr square, p theta square divided by r square, p phi square divided by r square sine square theta plus v. Okay, and you can obtain the Hamilton's equations. I don't have to go through all these steps. It's just taking a derivative. You can do that. You can try that, and yeah, you can get more practice. Now let's do one important problem, the Hamiltonian for a charged particle in an electromagnetic field. All right. Now in this case, we may not be able to do the same thing, t plus v thing. All right. So here is this is the place where we use all the steps in the proper way. All right. So the Lagrangian is given here. It's t minus. So this is the Lagrangian. We know this is the Lagrangian for charged particle in an electromagnetic field. All right, the summation over k vk ak, this simply means v vector dot a vector. Okay, the summation goes from 1 to 3. All right, it's just v vector dot a vector. All right, this is a velocity dependent potential, so you cannot simply write t plus v and then hope to get the Hamiltonian. So let's do it properly here, and first you find the momentum. All right, pk is dou L by dou vk, obviously, or px equal to dou L by dou vx, etc. Right? So you have a contribution from here, which is simply mvk, which is the usual momentum if there is no electromagnetic field. But now, in the presence of electromagnetic field, you get an extra term, which is qak. Okay, which is qak. All right. So generally we can say that p vector of a particle, charged particle in an electromagnetic field, is mv vector plus qa vector. Okay, it's not simply mv vector. Now we find the Hamiltonian. It's pk qk dot, summation over k, pk qk dot minus L, that's the usual formula. Okay, so that's equal to sum over k, pk qk dot. All right, so you need to multiply it with qk dot. Pk we already had, mvk plus qak, multiply by vk, so it's mvk square plus qak vk. So you are writing this in component form here. Okay, it's actually, I'm writing simply k, but this actually means that for k equal to 1, it's vx. Okay, v1 means it's vx, v2 means it's vy, and v3 means it's vz. All right, this is just a convenient notation, minus L. All right, so now you substitute this thing. This is summation over k mvk square. All right, so you can write as mv vector square if you want. Okay, because mv vector square is simply m vx square plus vy square plus vz square. That's exactly what you have here. Okay, so and this is qak vk. All right, this means ax vx plus ay vy plus az vz, which is simply a vector dot v vector. Am I right? Yes. So that's why I write it as qv dot a. Okay, so these two terms I simply write as mv square plus qv dot a. This bold letters here stands for the vector. Okay, minus half mv square. This is the Lagrangian. Okay, this is the Lagrangian that we write from here. Okay, minus half mv square minus q v vector dot a vector. So minus q v dot a here and plus q phi. All right. Okay, so there's we are just subtracting this term. Right. That's correct. So you see that these two terms get cancelled. These two terms get cancelled, and you have got half mv square plus q phi. All right. Now this is supposed to be the Hamiltonian, but are we done yet? No, we are not done yet, because you have got this v here, which is not good. We don't want this v here. We need only the momentum terms, all right, only the generalized momentum in this. All right, so we still have to make a substitution. So we already have this vk. Okay, so from here you see that vk is equal to pk minus qak divided by m. Okay, just solving this. This means that Vx equal to Px minus Qax by m, Vy equal to Py minus Qay divided by m, and Vz is equal to Pz minus Qaz divided by m. Right. So now we just substitute for V vector here, okay, and you get 1 by 2m Pk minus Qak square plus Q phi, or we can write there's a summation over k here. Right. So this means that this is actually P vector minus Qa vector whole square, P vector minus Qa vector whole square. Okay, I hope that's kind of obvious, because what we have here is summation over k. Let's pull this 1 by 2m outside. Okay, so what we have here is summation over k Pk minus Qak whole square. What does this mean? This means 1 by 2m sum over k Pk minus Qak multiplied by Pk minus Qak, right? And this means that if I don't want to put one term, would be Px minus Qax multiplied by Px minus Qax, okay, plus Py minus Qay multiplied by Py minus Qay, etc. What is this? It's simply the square of the vector P vector minus Qa vector dot P vector minus Qa vector. Right, so that we can write it as P vector minus Qa vector square plus Q phi. So that's the Hamiltonian of a charged particle in an electromagnetic field of charge Q. Okay, the charge of the particle is Q. Okay, now it's up to you. So I leave it to you as a homework to find the equations of motion. Find the equations of motion. Okay. So we have discussed the general method of obtaining the Hamiltonian. We have discussed general method of obtaining the Hamiltonian. We have also discussed the easy, the shortcut method, which works most of the times. Okay, except in the last case, we saw that in all cases we can simply write it as t plus v and then get rid of all the generalized velocities. Okay. Now we will have to do more problems of this sort. Actually, very simple problems have been asked in previous NET exams. All right, very simple problems which can be done immediately using h equal to t plus v. But you just be careful. All right, sometimes you may not be able to write it as t plus v, and you should know when you see the question, you should know whether you can write it as t plus v or not. Right. Now, if you are not sure by looking at the question whether we can write the Hamiltonian as t plus v, if you are not sure, then you can always use this method. All right, this always is correct. This is always correct. Okay, and make sure that in the end, all right, in the end, the final expression of your Hamiltonian, there shouldn't be any q dot. There shouldn't be any x dot or q dot or qi dot, etc. q1 dot, q2 dot, or x dot or theta dot. Such terms should not be there. Okay, no generalized velocity term must be present in the Hamiltonian. So you have to be careful. So after finding the final equation, all right, generally if you don't do this, it may be a mixed function of for example q dot, q and p, etc. So you should take care, you should be careful to get rid of all the q dot. Okay, so with that we'll stop today's session. I'll see you in the next class. Thank you.